And I hope this is the shortest video I ever make. All I want to do is point out the fact that when we have pure solids and pure liquids included with the gases or aqueous phase reactants or products, in this topic of general equilibrium, as confusing as it might be, the pure solids and the pure liquids are left out of the equilibrium constant expression. They're not written with the law of mass action. In some sense, we consider them to be incorporated into the constant. We could also say it would be hard to define the pressure, the partial pressure of a pure solid or the partial pressure of a pure liquid, or the molar concentration of the pure solid or the molar concentration of the pure liquid if we were writing a Kc. So, I don't know, it's hard to buy in the beginning, but it's always the rule that we almost never write the pure solid or the pure liquid as in the law of mass action. So if I'm leaving this out and leaving this out, all I really need to consider are the molar concentrations of H2O gas and H2 gas. So H2O goes in the top and H2 goes in the bottom. That's pretty strange. I guess if I wanted to write a Kp, it would be pressure of H2 in the numerator, pressure of H2. Oh, sorry, did I say that wrong? Pressure of H2O in the top and pressure of H2 in the bottom. So in a sense, I leave out the pure solid, the pure, whatever. Pure solids and pure liquids. Pure solids and pure liquids. Copper liquid, that's kind of a weird one. I guess I could imagine if it's hot, it would be hot to reduce the copper oxide with hydrogen gas in a flame. Yeah, could be. Cartoon. Yay, cartoons. In this cartoon, I'm depicting the calcium carbonate decomposition equilibrium with calcium oxide and carbon dioxide. And carbon dioxide, of course, is a gas. So if I were to, ask the question, what's the Kc, the Keq, Kc or Kp for this? It would just be simply, this one goes in the numerator. That's a pure solid, it's not included. And this is a pure solid as well, it's not included in the denominator. When I say not included, I mean just write a 1. So if I wrote, instead of this, I wrote a 1 in my constant expression, it would be concentration of CO2 times 1 in the numerator, and in the denominator it would be concentration of CaCO3 solid, but if it's a solid, just write a 1. So I wrote a 1 in the denominator as well. And as you know, there's no need in writing the 1 in the denominator if that's all there is. So I just wrote the concentration of CO2 gas, molar concentration or pressure constant. In this case, the Kp and the Kc would be the same. We'll have to talk about more about why that is later, but in essence it's because, no, that's a lie. Fiddlesticks. Okay, I'm wrong again. But anyway, so they wouldn't be different. They'd be different numbers. But the point here is this. It wouldn't matter if I had a little pile of calcium oxide and a big pile of calcium carbonate, or a small pile of calcium carbonate and a big pile of calcium oxide. So it doesn't matter if I have a little bit of this and a whole lot of this, or a little bit of this and a whole lot of this, as long as there is some of the solid there to establish an equilibrium, depending on this pressure here too. So if this plunger were to come down further or go up higher, then that might affect the partial pressure of CO2 and therefore affect the constant there. But as long as there is some solid there, I can establish an equilibrium. Fiddlesticks. Here we go. Another more bizarre idea is that I could possibly start out with no calcium oxide. So this could be totally gone, and I would have calcium carbonate at a particular temperature, perhaps a large temperature, perhaps a large temperature would allow these particles to break apart more to make some of this and some of this. So I could really just start out with a pile of calcium carbonate in a sealed container with no carbon dioxide, no calcium oxide. This equilibrium equation says that at least some of these particles will break down the forward direction to give some of these. As that happens, as I create some of this and some of this, then some of the backwards reaction would pick up faster and faster till the time where I eventually would reach an equilibrium. The warmer this container would be, the more this would break down to make more of this and more of this. But in any case, even if it was cold, I would still probably take some of this and go forward to make some of this and some of this. Even if it's cold, chilly, room temperature is kind of chilly for this reaction, I would still have a teeny amount of this and a teeny amount of that. And this calcium oxide wouldn't, if there were none of it in the beginning, it wouldn't separate itself out and form out in a separate pile. It would form right around the edges of where this calcium carbonate was initially present, so that I would have a mixture of calcium carbonate and calcium oxide in the same pile, but I would be generating a little bit of this on the edges of where this calcium carbonate is in contact with the volume space. Maybe it's airspace, doesn't matter. It's a crazy idea. But on the other hand, if I had no calcium carbonate, but only calcium oxide and no carbon dioxide, it would be like saying, let's take some of this and hope to establish an equilibrium. Well, you can't do it unless you had some carbon dioxide. If you had some of this and some of this and none of this, some of this and some of this and none of this, then the equilibrium equation says that this one and this one will at least a little bit come backwards to make some of this. So again, if I had a whole bunch of calcium oxide but no calcium carbonate, so none of this, some of this gas would react with some of the calcium oxide in the backwards fashion to create some calcium carbonate. So again, along the pile, near the edges of the pile where this is in contact with the carbon dioxide and the carbon dioxide is bumping into the calcium oxide, carbon dioxide is bumping into calcium oxide, it will create some calcium carbonate in the backward direction. So it would create some of this, but it wouldn't be in its own individual pile like this. This is turning out to be not the shortest video as I wanted it to be. Anyway, the bottom line, pure solids and pure liquids are left out of the equilibrium constant expression. They're actually in some sense contained within or wrapped up in the value of the equilibrium constant. There, I can shut up now. Practice that a little bit. See you soon.